Thanks, Mark. Welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. The agenda tonight is I have a few updates to give members of the Society, and then a slide on what we anticipate coming up over the next month or two, before we hand over to Dr Ciaran Beggan, who's going to talk about from swarm to Juno, and I'll let him tell you what all that's about. That will be followed by Mark this evening, who's going to give us the sky in February. Just a point, as normal, if you're on Zoom and you want to ask any questions, if you put them on the chat line, and we'll call your name out later, or Peter will, to ask those. If you're watching on YouTube and you're watching live, if you want to put those in the comments section, we'll try and peel a selection of those and ask them on your behalf. Thanks, Mark. Well, first of all, we have two new members, and if we could welcome in the normal way, we have Yoshit and Paul joining us. Welcome, welcome to the Society. That brings our membership currently to 137. Sadly, there are 14 people who need to pay their subs if they want to stay members, because the membership will lapse at the end of February. So just a reminder. Thank you, Mark. Our members should already be aware, but if you're not, the sad news is that Ron Livesey unfortunately passed away last week. Ron was the last recipient of our Lorimer Medal, which we awarded him in 2019. He was an extremely well-known and active amateur astronomer who for many years worked as director on the BAA's Aurora section, encouraging many people into astronomy and helping them both here and at Dundee Astronomical Society, where he was honorary president. Now, Ron's funeral will be held on the 15th, but with the usual COVID restrictions applying. However, the family are going to live cast the event, and details of that will be circulated to members. And we thought it only fitting that we'd put a link to the design of Ron's Jam magnetometer, which if ever you get the opportunity, Will has an excellent tale to tell about. So thank you, Mark. Coming up for members next Wednesday on the 10th, we have the Imaging and Observing Group. And on the 19th of February, we have the solar cycle, when Lynn Smith of the BAA will be talking to us about that. We've a members talk when Randall Stevenson will be talking to us about Thomas Hardy literature and astronomy, a slightly different tack on our normal talks, but sounding very interesting. Then on the 7th of May, we have Sam Lawyer, who's going to talk about the Outer Solar System Origin Survey, which sounds fascinating. And then the 20th, we have Catherine Hymans from Edinburgh, talking about the dark side of the universe. And if you're not familiar with us and you want to stay in touch, there's a whole variety of ways you can follow us, whether it's on our website, on Facebook, or on Twitter. And I'm happy to say that nearly all our talks since lockdown are available on our own YouTube channel, and tonight's will be no exception to that. So if you missed something and you want to catch it up, you're more than welcome to look there. Okay, Mark. And with that, I'm going to hand you over to Dr Ciaran Beggan of the British Geological Survey. So if you want to share your slides, Ciaran, it's all yours.
Hello. I presume you can all see that?
Yep.
Yes, all good.
Can you hear me? Yep. Great. Well, thank you very much for having me along. My name is Dr Ciaran Beggan, and I'm a senior geophysicist at the British Geological Survey based in Edinburgh. And I'm based in the geomagnetism group. And we study the Earth's magnetic field mostly, but we do take an occasional interest in other planetary magnetic fields. So tonight I was going to just talk a little bit about the Earth's magnetic fields and how we measure it, both from the ground and satellites, and how new measurements from a NASA mission called Juno at Jupiter is telling us a lot more about the planet and what's inside it, and how it's evolving over time. So as hopefully you all know, the Earth's magnetic field mainly comes from the center of the Earth, which we call the core field. But it's got other components as well, other sources which come from the rocks, for example, or space in the ionosphere, which is what causes the aurora shown in the background here. People often ask, well, what do we do with the magnetic fields? Well, the most obvious one is navigation. There'll be a magnetic field sensor embedded in your mobile phone, for example, and when you open a Google or Apple Maps application, a little map that the BGS make will be polled to see where you are, what your magnetic orientation is. So that's quite an important application. Other applications are mineral exploration. If you're looking for iron or other kinds of minerals, you can use a magnetometer. Probing right into the center of the Earth is something that we use the network of magnetic observatories around the world to do. And then we're becoming more and more aware of the hazards from space weather, which is what causes the aurora, particularly to satellites and ground-based technology, which is vulnerable to being damaged if there's a big geomagnetic storm. And if you didn't know, satellites also use the magnetic field along with gravity to orientate themselves in space as a satellite flies around the world. In terms of Jupiter's magnetic fields, it's still quite a mystery. We think it's mostly generated by a thin layer of metallic hydrogen high in the atmosphere, but it'll tell us something about the atmospheric composition over time. And it's also sort of a very rich environment. It's got lots of dust and plasma, which space physicists get more excited about than me particularly, but it is quite interesting. And then you can also use the magnetic field to find out if there's water on some of the moons of Jupiter. I'll mention that at the end. There's no known applications so far, but I'm sure someone will find one day. So I'll just start off with the Earth's magnetic field, tell you a little bit about that, a bit of history and why we study it and what we've kind of found out in the last few decades. And then I'll move on to Jupiter's fields towards the end of the talk. So here's some statistics about the Earth for you. The picture on the right is a sort of artist impression of the Earth's magnetic field as it sort of expands out into space. And the sort of fuzzy lines are meant to represent what's called a solar wind, which is a sort of continuous stream of particles emanating out from the sun. On the day side of the planet, the Earth's magnetic field gets sort of compressed into a bubble, and then on the night side it gets drawn out in a very long tail. That whole area is called the magnetosphere. So the Earth is, just for some numbers, it's about 6,371 kilometers in radius, so it's about 12,600 or 12,700 in diameter. If you were to weigh it, it's about 6 by 10 to 24 kilograms. And it rotates every 23 hours, 56 minutes and 4.1 seconds, because that's its rotation relative to the sun rather than the rotation of the Earth itself, which is obviously 24 hours. And then we normally use a coordinate frame called WGS84, which is sort of a best fit shape. It's kind of like a squashed football that best fits the shape of the Earth. The magnetic field itself is not completely aligned with the rotation axis. It's actually offset by about 10 or 11 degrees. And although the dipole moment, which is essentially a strength indicator, looks quite large, it's 10 to the 22 amps. When you divide it across the surface of the Earth, it's not actually particularly strong. We use a unit called nanotesla to measure the strength of the magnetic field, and it's between 23 and 65,000 nanotesla. And just for reference, a strong, say, fridge magnet will be about 10 or to maybe 100 times stronger than the Earth's magnetic field, which is why it's quite weak. It can only really turn a small compass needle freely. Anything beyond that, and its power is overwhelmed. And we know from hundreds of years of study that the magnetic field is generated in the outer core, which is about halfway or 55% towards the center of the Earth, which is why I've got this 0.55 RE shown. So it's the radius of the Earth. So basically the outer core is halfway to the radius of the Earth. And finally, the magnetosphere, this magnetic bubble that protects us, extends to about 6 radii, Earth radii, in the sunward direction, but it can extend 100 radii in the night side direction. And occasionally, very occasionally, the moon actually passes through the Earth's magnetosphere. But its shape is constantly altered by the solar wind. So it's a bit like water going around a rock in a stream. If you think about it, it's constantly shifting its sort of shape. Now, magnetism, of course, quite a venerable science, goes back hundreds, if not thousands of years. The Chinese were well aware of it thousands of years ago, but Europeans only became aware of it really in the 13th or 14th century when they realized you could use it for navigation. And they probably found that out from the Chinese. But of course, ship's compasses are the first thing people think of when they think of magnetism. And this picture on the right is a picture of the Discovery in Dundee. And the Discovery was a ship designed to go do Southern Hemisphere Antarctica research. And Scott was one of its famous captains. But the ship itself has a sort of bit in the middle, a kind of room with no iron nails. And one of the missions of the ship was to look for the South Magnetic Pole. And Britain has a long history of magnetic research, going all the way back as far as this man here, Edmund Halley. This image on the right is a picture of the kind of plaque on Westminster Abbey dedicated to his memory. And he was a man of many talents. I don't think I'll ever tick all these boxes. So he's a fellow of the Royal Society. He was sponsor of Isaac Newton's Principia book, editor of the Royal Society's journal at the time. He was also found time to be a professor in Oxford and so on. And you might notice a geophysicist there on this line here. And one of the things he was interested in was determining longitude, which of course was one of the major problems of science at the time. So at the time, around the 1700s, people could determine latitude fairly well by looking at the angle of the sun. But longitude was, of course, completely unknown because they didn't have accurate clocks at the time. So Edmund Halley, one of his ideas was to go and measure the angle between true north and magnetic north across the Atlantic Ocean. This angle of true north and magnetic north, nowadays we call it declination, but at the time it was called variation, which is why if you look on this map, you'll see west variation and east variation. And then along this line here, sort of running from the Carolinas across towards Cape Verde, there's a line that says line of no variation. And that's where Halley discovered that a compass aligns towards the direction of true north. And it's quite curious because it doesn't actually, as you look at it on the map like this, it doesn't actually point north. It kind of points at a very strange curve. If you're west of this line, or north in this case, then your compass points to the west or true north. If you're on the other side, it points east or true north. That's still the case today. Declination is still defined as being east or west or true north. The interesting thing about this map is it's the very first map ever known to show contour lines. So what Halley has done is he's joined dots of zero declination or zero variation and drawn a line to show this. And the report from the Royal Society meeting at the time, this was written down the bottom here, Captain Halley produced a map and showed his observation of the variation of the magnetic needle, which he rectified in the chart, as it was curiously laid down with marks, etc. in his map. And the curiosity bit is because no one had ever seen these contour lines before. So they thought they kind of cracked the longitude problem, but actually a couple of years later, Halley realized that this line had moved westward. And he realized that the magnetic field is permanently changing all the time on the surface of the Earth. And we know nowadays that roughly that line drifts towards about 20 kilometers per year westward in the Atlantic Ocean. So that meant it wasn't really any good for determining longitude because it would vary so much over the course of a few years that maps would quickly become out of date. Ironically, that same issue keeps me in a job, so I'm not too sad about that. And then finally, one of the things Halley noted was that there must be a layer of liquid in the center of the Earth to allow this to happen, to allow the magnetic field to vary. So over the years, people developed ground observatories. So these are locations around the world, normally in quiet regions, where they set up magnetic instruments. And here's one from Abinger in the 1930s. And essentially they would hang compasses on needles. And as the magnetic field varied, the needle would vary itself. And over time, it was automated, so they would shine a light on a mirror hanging on the compass, and that light would then sort of bounce back and forward across a room in a kind of light lever style, and eventually be recorded on photographic paper to create a trace of the magnetic field change across the day. So we still do the same thing in modern observatories. This is one of our BGS observatories in Heartland in Devon, And each one of these huts will contain a magnetic instrument or some sort of recording equipment. The house there at the top is where the sort of groundskeeper and the observer lives. But what they show basically is traces of the magnetic field changing across a day. And modern instruments are obviously more accurate than old-time instruments, but they still basically show the same thing, which is the trace of the declination angle across a day is about 1/10 of a degree. That's how much it varies on a quiet magnetic day. And horizontal and vertical intensities sort of vary in a similar way. During big geomagnetic storms, that variation in the UK can be maybe up to 5 degrees over the course of a few hours. So it can vary quite a lot more during a big storm. The modern observatory network looks like this. So there's around about 150 to 160 sort of professional observatories. The BGS run 10 of those. And you can see they're all more or less clustered in Northern Hemisphere and mainly around Europe, because it's obviously a sort of a science that requires a lot of investment. And you can see over the Pacific Ocean, there's hardly any observatories at all. So this leaves us with a big problem. Making maps of the magnetic field variation is actually quite difficult from ground observatories alone. So you need some other way to do that. You can make maps, and just to kind of give you an idea what these look like, here's a kind of modern version of Halley's map. And this green line is this line along which your compass will point towards true north. If you're in the blue zone, it points west. If you're in the red zone, it points right. Just to kind of make you note that if you live in, say, California, your compass points 10 degrees east. If you live in New Zealand, your compass can point 25 degrees east. You live in South Africa, your compass can point 25 degrees west. So it just so happens in Britain that our compass is more or less aligned towards magnetic north. But that's only coincidental. That line changes all the time. In terms of the field strength, this is what it looks like. So you've got the two kind of polar regions. The North Magnetic Pole actually has kind of two lobes, whereas the Southern Magnetic Pole down here is only got a single lobe. And then there's this area called the South Atlantic Anomaly where the magnetic field is abnormally or anomalously low. This is due to the way the magnetic field on the core where it's created is configured. If you look at how the magnetic field changes over time, there's a technical term for it called secular variation, and that's what geophysicists use. And secular variation just means the kind of slow change due to the core. So about 120 years ago, we made maps from observatories at the time and ship's records and so on, and observations made by geophysicists. So that's what it looked like about 120 years ago. And if you note, this region, the South Atlantic Anomaly, is not particularly obvious, but jump forward to kind of modern day, and you can see that that region has now grown quite substantially. I'll just flip forward and back there, just to give you an idea. So the magnetic field of the Earth is actually weakening and about 5%, maybe 10% per decade, depending on how you judge it. And it looks like it will continue to weaken for, well, at least another 50 years or so anyway. Okay, so where did the magnetic field come from? Well, there's been lots of ideas about how it's formed, but basically you all have to explain all these things, that the dipole part, so that's the main part of the field, the kind of bar magnet part, is most of the fields. It's dipped away from the axis. We know it can drift in time, and we know that reversals have taken place in the past. So people have proposed that the Earth is a permanent magnet, or there's electrical currents in the rocks. But actually, the process that creates it is this quite fancy term called magnetohydrodynamic processes, which basically is sort of a very fancy way of saying something like a bicycle dynamo. The geomagnetic field is essentially heat turned into motion, turned into electricity, turned into a magnetic field. And I'll show you quickly that in a second. So if you don't know, the Earth is a very obviously layered body, and you've got this core, the core about the size of the moon, you've got this liquid outer core about the size of Mars, and then you've got the kind of rocky mantle and the crust, which is the sort of very thin layer which we all live on and depend on, and that includes kind of all the minerals we get out of the ground and things like volcanoes and the plates that we live on, plate tectonics and so on. If you look at the center of the Earth, what creates the magnetic field is this liquid outer core, and it's basically about 90% nickel and iron and 10% other stuff. Other stuff includes stuff like oxygen, lithium, sulfur, that kind of stuff. But it's very electrically conductive because it's hot liquid metal, and it's about as runny as water is on the surface. So it's actually quite low viscosity. So if you look at your glass of wine or bottle of beer or whatever, give it a shake, and that's roughly how runny the liquid iron in the center of the Earth is. The Earth rotates once a day, so that keeps the whole lot spinning. And then the interesting thing is that this inner core is slowly freezing. And as it freezes, it's actually pure iron, or near enough pure iron. So as it freezes, it kind of squeezes out the impurities, these lighter elements, and they rise in a buoyancy fashion off the inner core into the outer core, and they stir the outer core a bit. So you've got basically all the things you need for creating a dynamo. You've got fluid that moves easily, you've got motion in 3 dimensions, and essentially, if you've got an existing magnetic field, it can get kind of wound up, and a magnetic field that gets wound up can create electricity, because electromagnetism is the same thing, and then that creates a self-sustaining dynamo. So this plot here just shows this dotted outer line is kind of the edge of the outer core, and inside the magnetic field, this is a computer simulation of what it might look like. You've got all of these magnetic fields all twisted up in a bundle, or like bunches of like wet spaghetti all stuck together. And that's a very complicated region inside the core. But once you get to the outer core, that all simplifies and starts to look more like a sort of very simple bar magnet. And that's what we see at the surface of the Earth. So a geodynamo is basically the heat and motion of the outer core creates electricity, and the electricity creates a magnet in the same way as a doorbell or a bicycle dynamo. Same physics. Now, what's interesting in terms of the Earth is that although the core generates most of the signal, you could actually look at lots of different geophysics and lots of different bits of the world based upon the magnetic field. So you can look at how conductive the mantle is. So those rocks, how much electricity they would generate, and that allows you to peer into the mantle. You can look at the crustal fields, that's the rocks below our feet that have permanent magnetization, and they tell you a bit about geography and the history of the Earth and plate tectonics. You can look at the ionosphere, it tells you about how radio waves will propagate through the ionosphere. The magnetosphere will tell you about the solar wind and the long-term solar cycle. You can detect tidal signals and so on. So without scaring you too much, this is just a geophysicist view of the Earth's magnetic fields. And actually, you know, what most people use is just really a small fraction of that. But if you're just in an observatory, you can only really see a time variation. Whereas if you want to see the global variation across the whole of the world, you need satellites to do that, because satellites will travel around the world and sample it very quickly over the course of a few hours, months, or years. So the thing about all these magnetic signals is that if you make a single measurement, you'll just get the entire summation or all of those signals in one single measurement. So how do you tease them apart if they overlap in time and space? Observers are good for the time part, and satellites can cover both, but they do have some drawbacks. So satellites are not the entire answer, but they are some of the answer. Now, previous satellite missions, there've actually been very few considering how kind of fundamental magnetic fields are. There was these ones called the OGO, or orbiting geophysical observatories. They are NASA missions, and they had very elliptical orbits and very basic sensors. They really only sense the strength of the magnetic field. There was a satellite called MagSat, this one here, it's the best drawing I could find of it, which was a dedicated satellite launched by NASA in the 1979 and 80. And that was very important for making the first global maps of the magnetic field. And you can see this little bottle at the end here, this little sensor, that was what measured the magnetic field. And it is about the size of a beer bottle, actually, because it's basically a sort of cylinder filled with typically something like petroleum or paraffin, wrapped with electrical coils around it. And you can excite the coils and measure the magnetic field based upon the response of the liquid. The modern era started in 1999 when the Danes launched this satellite called Ørsted, named after one of their famous scientists who had a lot of research on the magnetic fields. And they brought in this idea of a star camera. So they've got, this thing's about the size of a suitcase, and they've got this 8-meter boom, and 2/3 of the way along it, they've got a vector magnetometer that measures the orientation of the field. And they put a star imager on it so that it could stare at the stars, and you'd be able to orientate from looking at the star fields, the magnetic field measurement in 3 dimensions. And because this vector magnetometer sort of is not an absolute instrument, it drifts with time, there's a scalar magnetometer at the end of the boom, which sort of calibrates this vector magnetometer and allows you to make absolute values. Based upon that, and then there was another mission launched by the Germans called CHAMP, that lasted for 10 years, and that was sort of the next iteration of the Ørsted mission. It had 2-star cameras and better GPS, and they made a big effort to make it very magnetically clean so that the solar panels and electronics weren't kind of giving off their own magnetic field signals. And these led the way for the most recent mission, which is called the SWARM mission. So this is a European Space Agency mission, and it's been up and flying for the last 7 years or so. And if you've ever had any dealings with the European Space Agency, these guys don't do anything by halves. So this is like the Ferrari of magnetic satellites. It is the best of the best, and it's like a Ferrari in terms of price tag. It's very expensive. So what they have is a sort of very sleek looking satellite. On the front are like electric field sensors, got solar panels, GPSs, got a laser reflectometer for making measurements from the ground, so located very precisely. And then it's got this kind of boom hanging out the back with 3-star cameras, a very sensitive magnetometer here, and 2 absolute scalar magnetometers there. And so the whole mission is a kind of very high quality build, and they made a lot of effort to make sure it was magnetically clean. But again, being the European Space Agency, why buy one when you can buy 3? So they got 3 identical satellites, and the idea is that 2 of the satellites fly in a kind of lower orbit, side by side, separated by about 15 seconds as they cross the equator. And they kind of give you the magnetic field measurement between them. And then there's one at a higher orbit that drifts in different local times. So they've got a different orientation relative to each other. And that gives you sort of a third dimension. So it allows you to see what's happening across the globe. So you sort of got 3 dimensions measured. They're all in kind of polar orbits. So they more or less go over the North and the South Pole as they fly around. And they move about 7.8 kilometers per second. Now, the issue with moving that quickly is that when you make a measurement, there's an ambiguity, because if it takes 1 second to make the measurement, you've moved 8 kilometers. So if the measurement between your first point and your second point has changed, well, was that because the magnetic field changed or because you've moved position? So there's a slight ambiguity that you have to deal with the satellite measurements. Here's just some pictures of them putting it together, give you an idea of the scale. So I guess that's about the size of a bus when it's all extended. This is it being assembled before it gets launched in Russia. So they put the 3 satellites into kind of a nose cone configuration. You can see the booms are tucked away there. Then they put it in one of these Russian Euro rockets, or U rockets as they're called. And then it just blasted off on the 22nd of November in 2013. And once it was up in space, the idea was springs would force the satellites apart. They were quite worried that they might bang into each other in space, which would be, of course, catastrophic. But it all worked out quite well. And then the boom would deploy a few hours later and then lock into place. And then satellites would be on their merry way to make measurements. And of course, they all launched from the same rocket. So at the start, they're all in the same orbit. And then they used some of the fuel within the satellites to boost one of the satellites to a higher orbit. And because it's in a different orbital plane, slowly it will precess at a different rate to the other ones. So after 3 or 4 years, the upper one will move through a different local time, as it's called, compared to the other 2, and give us a sort of 3-dimensional view of the field. So, you saw that map of the observatories, and you see how few there were, 160. In one day, this is just a day I picked for 2014, the 3 satellites will have essentially sampled, a good third of the Earth. So over the course of about 4 days, they'll essentially sample the whole Earth many times. And even just basic on kind of very raw measurements, you can see that as it crosses the South Atlantic anomaly, the strength is quite low, but as it crosses the South Pole, the strength is quite high. So what can we do with this data? Well, in order to look at the core field, we need to throw away nearly all the data that's kind of bad. And this leaves us with kind of these selection. Green is vector data and blue is just using the scalar instrument only. And the idea is to reduce the noise from the auroral zones. And if you take that data, you can make a map of the magnetic field on the core mantle boundary. So this is at halfway to the Earth. The field gets stronger, so it's not just nanotesla now, it's about an order of magnitude stronger. And you can see the north magnetic polar region is quite complicated. The southern polar region is less complicated. And then where the South Atlantic anomaly is, you can see this blue area kind of inside the kind of orangey area. And that's called a reversed field flux patch. And that's what's creating the South Atlantic anomaly. The magnetic field in this region is starting to reverse, essentially. So as well as making snapshots of the field, you can also make maps of how it changes over time, the secular variation. And this bottom left plot just shows you the amount of data. The very thin line at the bottom is observatory data, and then all the other ones are satellite data. So you can see how satellites really contribute the bulk, 95% of the data that we use now. And if you look at the change of the magnetic field, you can see these large spots. So again, this relates to where the field is reversing most quickly along the equator. And this tells you a little bit about how the magnetic field is moving on the surface. And by using a bit of clever maths, you can turn that into a core flow. So this is how the liquid iron flows along the core mantle boundary. You see it's got this gyre in the southern Indian Ocean. It drifts quite strongly westward in the Atlantic. But actually, it doesn't really move very rapidly in the Pacific Ocean, which is quite strange. So the poles are moving. The red dot is the dip pole, so that's where the magnetic field is vertically into the ground. And the North Pole has moved very rapidly over the last 120 years, but the South Pole hasn't, and that's due to this way the magnetic fluid is flowing in the outer core. And to plot that as a sort of velocity plot, so that's time in the bottom and velocity in kilometers per year. The North Pole has been moving at sort of between 50 and 60 kilometers per year for the last decade or two. Seems to be slowing down now, but that's just an estimate. It might still remain the same speed, whereas the South Pole really hasn't been moving very fast at all. Okay, I talked about the crustal fields. That's the bit due to the rocks, and you can use this to look at the plate tectonics, for example. So you see over the oceans that the strength of the field is very low, whereas in the continents it's very high, and people use this to reconstruct plate motions over time. But to get to that, you've got to remove a lot of the other fields, the main field and all of the kind of contaminating fields. And you're still left with contamination in these regions around the northern and southern poles, because the aurora is just a very difficult region to get rid of. So you can use that to study geology, and geologists are really interested in these kind of maps. You could actually study tidal fields. For example, you can look at the lunar tide. So that's from the moon going around, that's from the Earth rotating, the moon moving very slightly every day. And you can see that in some regions of the world, the lunar tide is very high, and other regions it's quite low. So you can use these are maps that you can use to determine where the tides are strongest around the world. And then finally, you can look at the auroral features, part of the magnetic field you measure in the upper atmosphere. And this one with Steve has created a lot of interest over the last few years. So it's this kind of picket fence, kind of mauve purple colors, and it was quite mysterious. And it wasn't until around 2015, 2016 that amateur photographers sort of asked scientists what it was, and scientists didn't know what it was. So there was a large amount of research in the past few years. This is a picture from a camera on the ground looking up in Canada somewhere. And this thing marked at the bottom is Steve, and this green line is a swarm ground track going through it. So they used swarm to kind of find out what it was. So if you look at this plot here with VIE, so that's basically the velocity of the electric field. As swarm passes through Steve, which is this kind of pinky region, you can see that the velocity increases. And this T is temperature, so that's the temperature in the upper part of the atmosphere, and that increases as well. And then the density increases as well. So Steve has got a kind of quite an acronym which is strong thermal and electric velocity enhancement or something like that. So swarm has been part of working out what exactly it is. So it's still a hot topic. Okay, swarm is still going strong. It's got plenty of fuel. So if you look at this plot here, just look at AC, which is red line. If they did nothing, swarm will fall out of the sky in about 2 years' time. But they've got enough fuel to pump it up to about 500-kilometer altitude. And then if they do that, it'll last another decade. And similarly for Swarm B. So these are asking the scientific community what they want to do and how they want to configure the satellites, and in order to kind of make the most out of the science available. So it could well last another decade, in which case I'd be quite happy because it makes my life very easy. Okay, let's talk about Jupiter now. So Jupiter is obviously a very large planet, and it's got a large magnetic field to go with it. So just to kind of give you an idea of scale, to start off the top left here, here's the magnetic field of Mercury. which looks very similar to Earth in that it's sort of a kind of bubble squeezed on one side by the sun and pushed out the other side. But the magnetic field of Mercury is tiny and actually would fit inside more or less the Earth. Here's the Earth's magnetic field, and again that extends out into the solar wind. It's got a kind of similar shape, but the Earth's magnetic field is actually quite small compared to Saturn's magnetic field. So it would actually fit inside the rings of Saturn quite easily. So it gives you an idea of the scale of the planet as well as the size of the magnetic field. Here's Saturn's magnetic field extending out here, but Saturn's magnetic field would essentially fit within the first part of Jupiter's magnetic field. So Jupiter's magnetic field is absolutely enormous. And if you could see it with the naked eye, let me just show you here. You can see with the naked eye, from the Earth, it would subtend about 3 times the size of the full moon, if you could see the magnetosphere. So Jupiter's magnetosphere is first of all, the magnetic field that it generates is very strong, and also the solar wind at that distance is quite weak, so it's not really being buffeted in the same way as the Earth or Mercury is. So just some facts about Jupiter. Its radius is about 71,500 kilometers, about 11 times that of Earth. It's about 380 times more massive than Earth. And it's got a rotation period of 9 hours, 55 minutes, 29.711 seconds, plus or minus a little bit. And the coordinate reference frame is actually based on the magnetic fields. As Jupiter rotates every 9 hours, 55 minutes, gives off a kind of a predictable burst of predictable burst of radio waves, which are generated by the magnetic field. So in the 1960s, they set this up as the coordinate system. It's kind of similar to the Earth in that it's kind of got a 10-degree offset from its rotation axis. It's much, much stronger than the Earth's magnetic field. And the surface field is about 20,000 nanotesla. So a fridge magnet would stick to Jupiter were it to have a surface. Or you could maybe levitate fridge magnets if you're on the surface. It's got dozens of moons, and actually these moons are quite important for creating a lot of the geophysics you see around Jupiter. So the magnetic field is actually believed to be created by a thin layer, a sort of a shell at some depth, around about a quarter of the way into the planet. And that's where they believe hydrogen, which is primarily what Mercury is made out of, it gets compressed and squeezed, so it's not a gas anymore, it becomes a liquid. So unlike the Earth, where the iron is what creates the electrical conductive layer, here it's hydrogen, which is normally a gas you associate with balloons or putting in your super duper Back to the Future car. The moon Io, the innermost one, is the most active body in the solar system. It's basically spewing volcanic dust straight into space, and that dust gets swept up in Jupiter's magnetic field, and part of it gets charged and then creates an electrical current which flows along the magnetic field of Jupiter and impinges on its north and south pole. And as it impinges, it creates a sort of very bright aurora, and these aurora can be taken pictures of by the Hubble Space Telescope, for example. And you can see the one of Io here is a very strong one, and then you can see the other 2 moons, Europa and Ganymede, are also creating aurora as well. So because of this, you can actually use Hubble to study the magnetic field. And the other thing about it is that because it generates all these particles, it actually generates particles that are very highly charged, and so they're very dangerous to spacecraft flying through this particular region of Jupiter's magnetic field. So previous NASA missions have included flybys. There were the Pioneers in the early 70s. Then Voyager 1 and 2 went past in 79. And then there was a mission called Ulysses, which used Jupiter basically as a sort of, as almost a table tennis bat to knock it from the ecliptic plane, which is where the sun and the planets are, out and up over the sun. So that was able to study the magnetic field of Jupiter as it came by. And then New Horizons, which is more famous for visiting Pluto, went past in 2007. There's been a couple of orbiters. There's been Galileo, that's a very famous one, and nearly all the pictures you see of Jupiter and its moons come from Galileo. And then the present mission is Juno, which was arrived about 4 or 5 years ago. And then they've used telescopes to study the footprint of this moon on the aurora. So from all that, they've basically put together a magnetic field model of Jupiter, which you can see has got very low resolution compared to the Earth, for example. But because of that, they're able to say what the field looks like. So from all these flybys and the Hubble telescope, they're able to map out where the moons have their footprint. And so they can see that the magnetic field is tilted by 10 degrees. That's why we've got this large red patch here. Okay, so that was the best we could do before we got to Juno. Juno itself is, again, the size of a large car. Looks like about twice as long as a person, so I guess that's probably what, 5-ish meters. It's got 3 sort of axes, and it spins every 30 seconds. As it goes past Jupiter, it skims about 4,200 kilometers above the surface, and at that point it's roughly going about 55 kilometers a second, and then it spins back out again, and it goes out to about 8 million kilometers and comes back in again. So it's got a return period of about 53 days. If you look at the magnetic field mission, it's this bit here at the bottom, kind of out on a bit of an extra limb. That's to try and separate it a bit more from the satellite body and the solar panels, because it's not as magnetically clean as, say, SWARM is. So it's got 2 magnetometers, an inboard and outboard, to kind of try and get rid of some of the magnetic noise from the spacecraft. And you can see it's got these cameras, star cameras, so that they can orientate the magnetic field in 3D. It's very sensitive, so when it's kind of traveling between Earth and Jupiter, it could measure the solar wind very accurately. And once it got to the planet, it needed to sort of switch to a different mode in order to measure the magnetic field. And I could do that very, very accurately to about 0.5%, 0.5% accuracy. Okay, so the other thing about Juno is the reason for this kind of very long orbit is that it basically has to thread its way through these very high dose radiation regions around Jupiter. So it's got to get in as close as possible so it avoids that kind of dust and high radiation that Io generates right in around the equator of Jupiter. So it kind of runs in really quickly and comes back out again to give the satellite time to recover. And when they first launched Juno, they weren't sure it was even going to survive 1 orbit, but so far it's done 31, so that's really good. And you can see its orbit as it's gone in and out of Jupiter over the past 5 years, was try to sample Jupiter at different longitudes to get a better idea what the magnetic field looks like. Okay, so the first orbit they went through, they skimmed the surface and they released a profile about a year later. And this black line shows you the orbit. The kind of underlying blue and red colors are what the best magnetic model at the time was. And then they serendipitously passed near enough this big blue spot. So this is kind of a negative anomaly in the magnetic field, which nobody had known about at the time, somewhere along the equator. And of course, Jupiter has a big red spot, which is a storm in the upper atmosphere that's been around for, well, since the days of Galileo, 400 years now. And so they call it the Great Blue Spot, kind of jokingly, just to kind of like show the contrast. It's only blue because it's negative on this color scale. So was it real? Did it exist? So after another 8 orbits, they released this map. And this spot here, this anomaly, was still there. So what they found was that Jupiter's field is actually stronger than they expected. And it's actually asymmetric, meaning it's unbalanced. It's got more strength in the northern hemisphere than the southern hemisphere, which is a real surprise. So yeah, this blue spot is real, and all of the magnetic field is kind of covered. A large amount is concentrated in the north, which no one has an explanation for yet. So in actual fact, Jupiter's field is nothing like the Earth's, which was a surprise. Okay, this is just a map to show that. So here's the Earth, and if you remember, I showed you the magnetic field along the core a few slides ago. So essentially that's this plot here, and you can see that if you look at the dots, there's some bright dots at the equator, of course, but overall there's quite a lot of structure spread all across the planet. Whereas on Jupiter, all of the magnetic field is basically concentrated in the northern hemisphere. So nobody knows why. And the other thing is, it's been a long debate for many years. Does Jupiter's magnetic field change? Does it have this secular variation that we talked about in the Earth that's quite easily visible? And that kind of like put the kibosh on Halley's dream of longitude maps. So if it is low, or previously, if it was low, it was basically undetectable. But the problem was all the previous missions were kind of in Jupiter's equatorial plane. No mission has kind of flown over Jupiter's poles before in the same way as Juno. So it was hard to understand. And also this ambiguity because the the rotation of Jupiter is based upon the magnetic field. So if the magnetic field changes, it would look like a change of the rotation rate more than it would look like a change in the magnetic field. So there's this kind of ambiguity, and this small difference of 0.004 seconds means there's kind of wiggle room. So I'll show you a kind of more complicated slide in a second, but basically what these researchers did was to say, well, if all of those old missions had flown past Jupiter today with our new super duper up-to-date magnetic map from Juno, what would those missions have seen? And, you know, is the modern day representation of their flight path and the magnetic field they would have seen different from the kind of error on the measurements that they made at the time? So I'll explain this. So they took pioneers in the Voyager and Ulysses. So in this case, Pioneer 10, just let's look at the upper one, the dots are the magnetic field it would have seen had it flown past Jupiter today. And then the gray kind of bars, or gray kind of patch, is the error on those measurements. So you can see the dots pretty much fall within the error. But if you look at Voyager, it flew past and its dots are much more clearly distinct from the error on its measurements. So that suggests that, yes, there has been a change of the magnetic field of Jupiter between when Voyager went past in '79 and the modern field that Juno has measured. So that suggests that there is a change in the magnetic field. And I'm going to do one last kind of quite complicated slide just to kind of give you an idea of the flavor of what people are thinking in the kind of scientific community. So if you look at the surface of Jupiter, you can see the winds. You quite clearly see the winds blowing back and forward at different latitudes. You get this kind of mixing in these latitude bands. If you map those winds into the kind of motion, they'll either be blowing, say, west in this case, or east in that case. So they've got some sort of zonal drift is the technical term for that. What if the winds were to extend from the surface down into the depths of the planet? How would that change the magnetic field? So how would the wind drive the secular variation? So in Earth, the secular variation is driven by the flow of liquid iron in the core, but maybe on Jupiter, the magnetic field is driven by the winds blowing it across the surface or the subsurface deeper down. So that's what they did. And what they said was, well, the great blue spot is on the equator, and the equator is where the winds blow fastest in Jupiter. So will it change over time? And they made a prediction over here. If you look at panel B, here's what it looks like now. And they're saying because of the winds of Jupiter over the next 20, 40 years, this blue spot should break up into maybe 2 or 3 different blue spots as the different winds on the surface blow it. So the exciting thing is, if this is true, it should be visible by the time Juno finishes its mission, maybe in another 5-10 years' time. Okay, so Juno's future. So it's completed 31 orbits. The original mission was 16, and then it got extended to 33, and we're almost at 33. And now it's been extended for another 5 years to 70. But the exciting thing is they're going to start reducing the apogee, so the furthest point, so that they can start to explore the moons of Jupiter. So Juno should be able to make several passes of each of these moons and try and detect any magnetic field variations as it goes past the 3 moons, which is quite an exciting thing to look forward to. Okay, so what's Juno shown us so far? Well, it's shown us that Jupiter is quite different from Earth. It's got this kind of weird, everything's concentrated in the northern hemisphere. It's got very strong polar aurora, which are stronger than expected. Its gravity field is lopsided as well. Again, it concentrated in the northern hemisphere for some reason. It may have a fuzzy core rather than a solid rocky core. It may have something a bit more kind of nebulous. And maybe these winds are driving the magnetic field change. And then lightning apparently is also stronger than the northern hemisphere, although that might just be a seasonal effect because the northern hemisphere is in summertime in Jupiter at the moment. Okay, yeah, so just to kind of a couple of conclusions. So I hope you've got the idea that studying the Earth's magnetic field and with ground observatory satellites is kind of very useful, not just for navigation. And the thing is, all of the fields are interconnected. So if you make improvement in one, you can improve the other. So it sort of iteratively gets better and better. Although satellites are great, you know, you also need ground observatories to make sure that you can sort of tie the variation of magnetic fields over longer terms. And in the future, things like the aurora and space weather will become more important. as we've kind of become more dependent on technology. So yeah, then just Jupiter, our Jovian studies are in their infancy. We've actually got more questions than answers now, so that's good. Keeps everybody in a job. But a lot of the stuff I've shown you is built upon what we did on Earth, applying it across in Jupiter and to Jupiter data. So just to finish off, maybe Juno would help us answer the ultimate question: is there life out there? And we know that Europa has very likely a large ocean, but we don't know how big the ocean is because there's been no really good measurements of it. There were some from Galileo, but hopefully with Juno passing Europa, it will be able to make much better magnetic field measurements because the magnetometer in Juno's is so much better. Okay, I'll leave it there. Thank you very much for listening.
Oh, thank you for that fascinating talk. Can we put our hands together? Thank you.
Thank you very much.
Excellent. And right, do we have any questions, Peter?
Well, we've got Carl first. Carl, would you like to ask your question?
I would. Thank you very much for your talk, Dr. Beggan. That was very good. Thank you very much. I was interested when you said about the south, the polar anomaly at the south. Have you any idea what's causing that, or?
There are people who do geodynamo modeling or dynamo modeling, where they got very complicated computer models of what is happening, and that they can kind of recreate that, but you know, it's just a computer simulation. And it could well be that, and this is purely speculation, that, you know, some parts of the shell are, you know, not complete, for example, and so maybe hydrogen is, you know, differently concentrated in different parts of the planet. I don't know. That's one explanation, but in reality, no one's sure.
So do you see plate tectonics or anything else? Does that come through in your magnetic data?
On Earth, you mean?
Yeah.
Yeah. You can see that with satellite data. I mean, it's most clearly visible in the oceans. You can see the mid-ocean ridges and the sort of spreading of the ocean floor from satellite data.
Okay, thank you very much. Thank you.
Being a sailor, am I going to lose my ability to sail before long?
No, we'll keep you updated. You just have to update your map every year rather than every 10 years.
It seems to be accelerating rather speedily into Russia at the moment.
Yeah. So the North Magnetic Pole has moved, something like about 50 kilometers per year for the last 20 or 30 years. So it used to be sort of for the last 300 years or so, it's been basically hanging around northern Canada. And the last time it was visited in person was by one of the Canadian Geological Society geophysicists in 2007. By that point, it was just about reachable by airplane. You could survey it manually. But beyond that, it's now moved across the Arctic Ocean towards Siberia. And it's a combination of the flow of the outer core and the fact that the part of the field under Canada is weakening while the part of the field under Siberia is strengthening. So it's sort of pulling the magnetic pole towards it.
Okay, thanks for that. Jonathan Smith, do you want to ask your question?
Yes, I was interested about you describing the iron solidifying into the inner core from the outer core. Does the latent heat released by that, is that significant? Because I was sort of told that it was the radioactive decay was the part of the heating inside the center of the Earth.
Yeah, good question. So there's a couple of things going on there. Yes, the latent heat will contribute a little bit, but this core is, the heat is very uniform across the whole lot. So it doesn't stir particularly efficiently by heating alone. We believe this gravitational stirring is 90 or 95% of what causes the variation kind of in the radial plane, kind of away from the outer core, or the inner core to the outer core. The radioactive heat, because it's kind of blanketed by the mantle, the heat is trapped in particularly well. So it's cooling very slowly, and some of the reason it's cooling slowly is because of the release of latent heat. But we believe the majority is the release of buoyant elements, and that's what drives most of the core convection.
All right, thank you.
Okay. Andrew Mackey has 2 questions.
Thanks, Peter. I have a lot to learn. 2 questions, please. could you briefly define metallic hydrogen that you referred to, both in terms of the Earth and Jupiter? And secondly, can you square me up on the difference between the 10, 11 degrees that you showed of the dipole from the rotational axis in both the Earth and Jupiter, and what I see in my map as being what I call magnetic variation of being like 2 degrees going down to 0, please?
Yeah, okay, so sorry, I think I got a bit confused there. So it's metallic iron and nickel in the core of the Earth, and that's what creates the geodynamo. On Jupiter, it's believed to be metallic hydrogen in a thin shell around about 0.75 or 0.8 Jupiter radii, and that's where the Jupiter magnetic field is created. In terms of the magnetic field of the Earth and the tilt. So if you look at the part of the magnetic field that is purely created by the dipole, which essentially is the bar magnet part, a bit that we can describe as a very simple bar magnet, that is tilted by about 10 or 11 degrees away from the rotation axis. When you add in all of the other bits that are the non-dipole part, as we call it, created by all that complexity on the core mantle boundary, then that all adds up to creating a different location for the dip pole, and also for creating kind of this very complicated looking shape of the declination angle, the map between true north and magnetic north. So all of that together combines to make your compass, wherever you are, point generally in a different direction between true north and magnetic north.
Thank you.
I think, Jonathan, you got your bit in, didn't you? Or did you have a follow-up? No, you're okay, right. Well, in that case, I think we're finished. Unless there's any more questions from the Zoom team, we can go over to who's dealing with the YouTubers today.
I've been monitoring the questions here. We've just got a couple of questions. I think you've kind of answered the first one, but we'll just go ahead anyways. From Andrew Ramage, could Jupiter's field be caused by a core of liquid hydrogen rather than a layer near the surface, near the top? Is that a possibility, or is that something which just couldn't happen?
I don't know. I guess it's been discounted over the years. All the scientific literature suggests that this is where between 0.75 and 0.85 radii, Jupiter radii is where the magnetic field lies. There was a slide I didn't show, which sort of shows as Juno makes more and more measurements, we'll be able to narrow down exactly where that region is. At the moment, it looks like it's 0.8 Jupiter radii. I mean, I think any magnetic field which is created deeper within the planet is maybe shielded by this upper layer, or is so small as to be invisible. I don't know. You'll have to look at the scientific literature yourself if you want a bit of a deeper answer on that. Sorry.
Okay, that's fantastic talk. And we've just got one more from from AC. During polar reversals, would you expect to see several smaller mixed magnetic blue and red spots on the Earth? Sort of.
Yeah. So that's believed to be the way the magnetic field reverses. It takes between maybe 1,000 to 10,000 years. And what happens is that rather than being a kind of simple flip, the dipoles, or the main north and south poles, basically vanish. And then you're left with lots of smaller poles, which sort of will drift around the planet for a few thousand years. And then slowly the magnetic field will coalesce back into a reversed version of itself. So yeah, probably, if you were to live through one of these, you just have an aurora, maybe anywhere, possibly even down at the equator. And it would keep someone like me in a job, because we'd have to keep track of all these things.
Fascinating, thank you.
There's an upside to everything.
Yeah, well, for some.
Any more questions? Are we good? Well, can we just thank Dr. Ciaran Beggan again? Thank you very much. Absolutely excellent talk. Thank you.
Thank you.
Wonderful. And can we move on to Mark then, please?
Okay, so let me reorganize my screen. Can you see that?
Yes.
Yep. Okay. Okay, the sky in February. I'll talk about this nice picture by Frank Goodman a bit later on in the talk, but it's rather a nice one, I think. So let's start with the planets in February. Start with the excellent chart by Dominic Ford from his InTheSky.org website. Mercury, Venus, Jupiter, Saturn, all really too close to the sun's glare at the moment in February to be much of interest to us. So the two, you can see that they are on the far side of the sun from where we are on Earth. Mercury is coming slightly further away from the sun, but is also really low in the sky. So I think this coming month that those planets are not of much interest. The two planets that are available to us, though, are still Mars and Uranus, which are in the evening sky. Mars is obviously very topical this month. A year ago, 3 missions launched, and they're arriving at March this month. So the United Arab Emirates Hope Orbiter is due to arrive on the 9th of February in orbit. The Chinese Tianwen-1 is due to arrive in orbit on the 10th of February, but I think they're not planning to land that until maybe April or even May, until they find a suitable landing location. And then there's the Perseverance rover, which is due to straight to land on the 18th of February, and it's taking with it the Ingenuity helicopter to test that out on Mars, which should be a fascinating study to see what's happening there. So I'm sure we'll hear a lot more about those over the next month. Mars, that's what Mars was like in October when it was at opposition. It was 22 seconds of arc large and minus 2.6 in diameter. Really nice object over the last few months. Sadly, it's now getting further away, and it's less than a third of the size and quite a lot fainter as well. So it's still there, still obvious in the evening sky, but not such an easy object to observe through a telescope. I know I've bored you all with my Mars images over the last few months, but this is someone I've been following over the last since last summer, really. Martin Lewis, who's down in St. Albans, has given me permission to use his images for this talk. He's a BAA member and really knows how to image Mars. And using images such as that, he's actually created his own map of Mars, and I think that's absolutely fantastic what you can do with amateur instruments. He's using a 444mm Dobsonian telescope down in St. Albans. I think he made it himself as well, and you can see an awful lot of detail in the Syrtis Major, Olympus Mons, the Tharsis Ridge volcanoes, and loads and loads of other detail. I think that's quite an impressive piece of work by Martin there. Something I discovered today. 7th of February is Martian New Year. I didn't know it had a new year, but apparently year 1 was designated after an important dust storm in 1956. So this is the start of Mars year 36. I suspect it's been going a lot longer than that, but those are when records began by us, I think. It takes 668 sols to go around the Earth as opposed to around the sun as opposed to ours 365. But there we go. So we can celebrate Martian New Year on the 7th of February. If you're looking for a celebration, as we're trying to find lots of celebrations during lockdown, it keeps us happy. So that's another one we can have. Uranus is the other planet, less than half the size of the apparent size of Mars, and quite a lot fainter, probably just about beyond naked eye visibility. But you should be able to find it in the night sky with binoculars, and it's quite a useful skill to be able to hunt out things like that. You'll be able to make out its pale bluish green, very small disk, I think, with a small telescope as well. Not a lot to be seen on Uranus, but amateurs can actually take some very nice images. This again from Martin Lewis. You can see some nice shading variations on the surface there, and 5 moons are visible around about it. So I think that's quite impressive. Moon phases this month. So we have new moon around about the 11th and full moon towards the end of the month. Just a reminder that we have our AAC 24 introductory objects for beginners, and objects 1 to 4 are on the moon. You'll find information about that on the website. So here's an image I took around about full moon. As you can see, the the darker areas, the seas, the volcanic lava plains, and the large ray craters stand out really well at this phase. There's Tycho down there in Copernicus with the ejecta spraying all over the moon. The Tycho's ejecta really dominates the whole of the southern hemisphere of the moon there. But if we look at, say, half phase and look along the terminator, the crater Clavius is much more prominent. And here is the crater Tycho again, which just looks like a very ordinary crater. So at the different phases, you can see a lot of different features, full moon for the seas and the ray craters, and at most other phases along the terminator for more detail in the craters and mountains and so on. Definitely worth looking at the moon. It's, I mean, not a lot changes on the surface, but with a difference in light and shadow, I think it's a fascinating object to study. Moving to the sun, we are at the start of the next solar cycle, solar cycle number 25. And we have seen more activity on the sun recently. That's the prediction of what this next 11 years might look like. And just a reminder that on the 19th of February, we have a talk about the solar cycle by Lynn Smith, who's the director of the solar section of the British Astronomical Association. So she'll be able to give us a lot more detail on solar activity. Here are a few pictures that members have taken. This one by Horst last November when we had some nice spot groups on the sun. This one by me at the end of December. And I think the Arty Photo of the Year award goes to Will, with not the partridge in the pear tree, but a pigeon in a beech tree in front of the sun, and you can actually just about make out the sunspots there as well. But I think that's quite an arty picture, Will. Well done. Talking of solar activity, we've had some aurora recently, and our intrepid aurora chaser, Fran Goodman, took this one, I think, Aberlady Bay. Really nice picture. A couple of pictures there. I think the clouds help to highlight the aurora stand out in contrast. Really good. Hopefully we'll get more of those as there's more solar activity over the next few years. And Tosh White has spent the summer drinking beer to make his beer can solagraphs. So basically a beer can with a pinhole and photographic paper inside. He left it from the summer solstice to the winter solstice to get some amazing pictures with nice foreground objects. Quite a retro look to them, but really, really fascinating. The trees stand out really well. This is what they look like, and I think you have to admire his dedication to being prepared to empty so many cans of beer to do this. He says he empties it down the drain, but I have my doubts about that. But they are very effective anyway. So maybe he'll tell us about them at the next Imaging and Observing Group meeting, and then we can all drink beer. I mean, we can all make some as well. Just a reminder that we've recently started a project in the Society, the Messier project, where we're going to try and effectively as many of the objects in the Messier catalogue as well. I thought I'd do tonight, as we're going through the star charts, is I'll point out where major groupings of different Messier objects are in the night sky. So I've chosen looking south, about 9:30 in the evening in the middle of the month as the standard here. Down here we have, you can see that or not, we have Orion dominating the southern sky as usual. If we take the usual guide of the three stars in the belt, take it up to Taurus, and then we get up to M45, the Pleiades, one of the Messier objects, one of the more famous ones. This one taken recently by Pat Devine, very nice. Blue stands out really well. And we follow the line of the belt downwards, we get to Sirius, the brightest star in the sky. Around about this area, we have quite a number of open clusters. There's quite a handful down there in Canis Major and Puppis and Monoceros, that's how you pronounce it. Here's one by Pat Devine of M46 and M47. And if you look closely, you can actually make out a little planetary nebula in there as well, which is quite nice. Further up in the southern sky, higher up, we have Auriga with its 3 Messier open clusters, M36, 37, and 38. But I won't go into that just now because there is an article on our website, Explore Auriga the Chariot here, and it explains a bit more what's in Auriga as well as other objects, not just stark open clusters, but nebulae as well. Slightly further east, we have Cancer, the crab, with its 2 open clusters there. A couple of images by members, Nigel took M67 and Horst M44. Open clusters are just bunches of stars, but I think they're really interesting. The colors are different. The structure and layout of them are different. The density is different. You can see those 2 clusters are very different. And you don't have to mess around with nebulosity and try and pretend there's nebulosity there when there isn't. You know, I think open clusters are what they say they are, a bunch of stars, but very interesting nonetheless. And further over towards the west, there's Perseus high in the sky, and that's one I took a couple of weeks ago. M34 is quite a large open cluster. And further over to the east, Leo is rising, and over the next couple of months will be higher in the southern sky, and it's got a handful of nice galaxies in there as well, Messier galaxies. I won't talk any more about that now because I'm sure Alan will be talking more about that next month or future months. For this evening, I thought I'd concentrate on one constellation, Gemini, which is nicely placed high up in the south at the moment. And the 2 main stars, Castor and Pollux. Down at the end here, we have 35, another open. Horst also managed to pick up another open cluster, NGC 2158, down there as well as a bonus. Zooming into this end a little bit closer, there are other objects that aren't just Messier objects. So we have the 443, and we have 3 nice images, one from Ian, Horst, and myself. It's a supernova remnant, 5,000 light years away, and it's pretty large in the sky. It's faint at magnitude 12, but at 50 arc minutes across, that's how it compares to the full moon. So a pretty large object, that. One for the images, though, at that faintness. And also we have the Monkey Head Nebula, which I always assumed was part of Gemini. But as I was doing this, I realized it's actually part of Orion. I still associate it with Gemini because it's closer to the major stars of Gemini than it is to Orion, but it is actually part of Orion. Again, quite large at 40 arc minutes across, larger than the full moon, and quite a bit brighter at magnitude 6.8. And here's some images of that as well. The one on the right, mine is in narrowband, so that's false color in hydrogen alpha and oxygen 3 and sulfur 2. That's why it's different colors. There's one other object of interest I can think of, which we call the Lion Nebula, but it has normally been known as the Eskimo Nebula or the Cloud Nebula, but the IAU discourages us from using that now because those terms are apparently insulting. So we like to call it the Lion Nebula now. And it was a planetary nebula discovered by William Herschel. Quite small, 48 arc seconds across, not minutes, but seconds at magnitude 10.1. But we're used to looking at M57, the Ring Nebula in Lyra, and that is 78 seconds across. So it's a bit smaller than that, but not that much. And it's not that much fainter. So go and have a look at it. It won't look like that unless you have Hubble. Hubble will be going up for sale very shortly, I'm sure. So put your bids in. So we've spoken a lot about M, NGC, and IC, these catalog designations. I thought I'd say a little bit about that. So the Messier catalog we've spoken about already. Charles Messier, French astronomer, listed 110 or 109 objects, depending on who you believe. Not because he was interested in them, but because he was a comet hunter and he didn't want to confuse these objects with comets. So really a back to front use of a Messier of a catalogue, really, but probably the most famous one, and amateurs know a lot of the objects in there. NGC is very commonly used, the New General Catalogue. That was put together by J.L.E. Dreyer, who was a Danish-British astronomer, did a lot of work in Ireland as well. And he created a catalogue with 7,840 objects in there, as commissioned by the Royal Astronomical Society. And that really built on the work of the Herschels. So brother and sister William and Caroline Herschel created a catalogue of nebulae and clusters of stars, the CN catalogue, and William's son John created the general catalogue of nebulae and clusters of stars. And Dreyer really built on that. He was going to just extend them, but I think he was asked by the RAS to actually create a new catalogue, but he still had to build on that. He then added 2 sets of editions called the Index Catalogue, and he added them in 2 separate sets, and 5,386 objects were added to that as well. So NGC and IC you'll commonly see on star charts as well. And there is one other that we as amateurs use, really. It's really an amateur catalogue, and that's the Caldwell catalogue, as defined by Patrick Caldwell Moore, as he was properly called. It really is an amateur catalogue, and he listed 109 popular amateur objects to complement the Messier catalogue, things that he thought were left out. He obviously didn't think M110 was part of Messier's catalogue. And it includes favourites such as the Bubble Nebula, Rosette, Cocoon, Veil Nebulae, Double Cluster, Hyades, and a few galaxies as well. So all quite famous objects that we know quite well. And that's Patrick Moore receiving the Lorimer Medal in 1962 from our president then, Sheriff J.E. Forsyth. That's in our archives. So the twins themselves, Castor and Pollux. Castor is quite an interesting star. It's a 6-star system. That's 3 binary stars performing an interesting dance around each other, 61 light years away. The A and B components, or binary components, are about 6 seconds of arcs apart, so you should be able to see them in a small telescope. The C component is further away, but quite faint at magnitude 10, so not so easy to do. And those are the that's the size comparison. Our sun on the right, the A and B major components are quite large stars. The others are reddish dwarfs, I think. Pollux, it's a single star. It's a red giant. It's run out of hydrogen to convert to helium, so it's now fusing that helium into carbon and other elements, the sort of elements that we're made up of. But it does have an exoplanet. Thestius, its name, orbits the star every 1.6 years. If we look to the southwest, on that date, I can't actually see what the date is because it's hidden behind my controls, but you can see it anyway. That date, that time. There'll be a nice conjunction of Mars and the Moon, separated by about 3.5 degrees, and the Hyades and Pleiades are close by. So 18th of February at 7:45 in the evening. It's a good time to look at that. So for you wide field images, it might make quite a nice composition there with Mars and the Moon close by and those 2 star clusters. Hopefully the Moon shouldn't blot too much of that out because it's less than half phase, so it shouldn't be too bright. But it could be a challenge. So looking north at the same sort of time in the middle of the month, over to the west, going down towards the horizon, we have Andromeda, the Andromeda Galaxy, and M33 that we've seen a lot more of over the last few months. And there's M33 by Ian Smith, very large galaxy, large angular diameter. We've got Ursa Major starting to rise, and it'll be getting higher in the sky over the next few months in the evenings, and quite a lot of Messier galaxies there we can see. Here are a few that members have taken. Nigel Gooden got M106. I got M108. There's also a nice planetary nebula, the Owl Nebula, M97, just about there, which Nigel also got. And that's M82, the Starburst galaxy, the companion to M81, Bose galaxy as well. So there's a lot of nice galaxies in the area. Obviously, there's M51, the Whirlpool galaxy there as well. So that'll be getting higher in the sky, and these will be well placed to observe and image. And slightly further to the east, we have the Coma group of galaxies. That's starting to rise in the east and get higher as Leo gets higher as well. So loads of galaxies in there as well. Here's a nice picture of M87. I think that's it down the bottom, the one with the black hole that was imaged last year, and a Markarian chain of galaxies. Mike McGovern got that. Nice image there. So over the next few months, galaxies will be coming center stage in the southern sky. Maybe we'll be seeing lots more images of them from society members. And that's the end.
Thank you, Mark. Okay, well, that's fascinating. Plenty to for everybody to have a go at, particularly in the imaging observing group. But if you're not imaging, then even with a pair of binoculars, you'll be able to look at quite a few of those objects, particularly the moon, where people tend to dismiss it, as you say, and there's so much to see. So just a reminder about what's coming up. We'll leave that on the screen, and I think that's the end of tonight's proceedings. So thank you very much for joining.